Friends, you are welcome back to this second part of the lecture, Fuzzy Logic Why and What. In the first part we explained that why the concept of fuzziness is required, particularly in the context that in everyday context most of the problems involve imprecise concepts. In order to handle the imprecise concepts, the conventional methods of set theory and numbers are insufficient and need to be extended to some other concepts. Fuzzy concept is one of the concepts for this purpose. In the process we discussed a number of things, including the operations on the conventional sets which we call crisp sets. And then we said that these concepts need to be extended to fuzzy sets in order that fuzzy sets can be used as tool for solving problems. In that context we define what is meant by equality of two crisp sets or conventional sets, what is meant by subset or superset of a given set in the conventional set theory, and so on and so forth. So now in this lecture we will discuss how these notions or concepts can be further extended to fuzzy sets. So let us recall what is meant by equality of two sets in the conventional sense. In the conventional sense, two sets A and B are equal if every element of A is an element of B and every element of B is an element of A. Also we said that in the case of fuzzy sets, we not only write the names of the elements, rather we write the names of all the elements from the universal set, but we associate degrees of belonging with each element. So in this particular case, how the concept of equality for fuzzy set should be defined. And the natural way is that for each name or object in the two sets, we compare the degrees also. And if the degrees associated with a particular object in the two sets, two fuzzy sets, equal, and it happens for all the elements occurring in the two fuzzy sets, then we say two fuzzy sets are equal. However, if degree even for one particular element differ, then in that case we say that two sets are not equal. So exactly this idea is explained through the example or illustrated through the example which is given on the slide. Let us have a look at the slide. Now we say A is the set in which Mohan, Sohan, Johan and Ibrahim have different associated degrees. In B also the same four names occur with some associated degrees. There is another set C in which also the same four names occur with associated degrees. Just as I explained now, that two sets A and B as fuzzy sets will be equal if the associated degrees with a particular element for all elements equal. So you can see Mohan has degree 0.2 in set A and Mohan has degree 0.2 in B also, though the element Mohan occur at two different places, different orders in A and B, but which does not matter. You can see similarly for Sohan the degree associated is 1 in A as well as in B, and rest of the two elements. So in this way the two fuzzy sets A and B are equal because the same four names are occurring in the two sets, and not only that, for each name occurring over there the associated degree in the two sets is same. However, if we consider A and C, then you can see that Abraham has degree 0.2 in C and Ibrahim has associated degree 0.4 in A, and just by comparing the degrees of even a single element, if it does not, the degrees don't equal, we can say the two sets are not equal. We need not consider the degree of the other elements, just we should point out for a particular element the associated degrees differ, and therefore we can say the two fuzzy sets are not equal, and in this particular case the two sets A and C are not equal, because for at least one element Abraham, the associated degrees in A and C differ. In one it is 0.4 and the other is 0.2. I hope the concept of equality of two fuzzy sets must be equal and must be clear by this example. Now we will consider the concept of subset or superset. Friends, as I mentioned earlier, we are just generalizing the concept of set, which at present we are calling Chris set, to fuzzy sets. Now in the normal or Chris sets, what do we understand when a set A is a superset of a set B? There it is very easy. If the elements in A include all the elements in the set B, then A is said to be a superset of A. But in the case of fuzzy sets, we know in each fuzzy set all the elements of the universal set are included. So how do we know, or how do we define a set as a superset of another? But in the case of fuzzy sets, we know, despite the fact that all the elements of the universal set occur, the associated degrees are different, and the associated degrees actually are degrees of belongingness to a particular set. If I say that Johan is 5 feet 9 inch and a person is definitely tall of 6 feet, then we say Johan is nearly tall, very good possibility. Degree of tallness is 0.7 in that particular case. So what I mean to say, the more the degree, more the belongingness to the particular set is there. So what may be the criteria for supersetness in the case of fuzzy sets? The supersetness may be determined or may be defined among the fuzzy sets by comparing the corresponding degrees of each element. And if it happens that for fuzzy set A, the degrees of each of the elements, degree of each of the element in A is more than or equal to the degree of the corresponding element in B, we can think of A as a superset of B, because we have said just now that degree is actually a measure of belongingness. More the degree, more the belongingness, and therefore it very precisely captures the notion of superset in the sense more the degree, more the belongingness, hence more the setness. More the setness means more the set is superset of the other set. Similarly, subset can be defined if for each element, if we compare the degrees and the degrees of the elements are less in B as compared to the corresponding degrees in A, then we can say B is a subset of A. So we just capture this notion in a formal way. Another thing which may clarify the definition of superset is the example that when we say set of all tall people, and at the same time we consider the set of all very tall people, then our common sense says the set of all very tall people should be a subset of the set of all tall people, because every very tall person must be a tall person also, and therefore the set of very tall people must be a subset of the set of tall people. It can be formalized in the form of fuzzy sets as is given on the slide. Please read the second part. If the degree of tallness of a person is say 0.5, then the degree of very tallness should be lesser, that is 0.3. Because when we are saying the degree of tallness is 0.5, naturally when we are considering very tall, for example, if a person is tall, if he or she is, he is above 6 feet, and we will say a person is very, very tall or very tall if he is above say 6 feet 6 inches. So the degree of very tallness reduces in the process because more height is required to be called a very tall person. So we use these two ideas. The first one is the set of all very tall persons is a subset of the tall persons, and number two, the degree of very tallness reduces from the degree of tallness. So using these two ideas, we try to define what is meant by superset. Please look at the slides. That is, let us take X is the universal set, and we are given two sets A and B. We are trying to formalize the concept of superset. So in which x1, x2 up to xn are the elements of the universal set which occur in both of the sets A and B. How the degrees v1, v2, vn in A may be or equal to or different from the degrees w1, w2, wn which are associated with the elements x1, x2, xn respectively. Now we will like to define as is A as a superset of B. What we should say? We should say A is a superset of B if for each Vi is greater than equal to the corresponding Wi. That is, V1 should be greater than equal to W1, V2 should be greater than equal to Wn, W2, and so on, and Vn should be greater than equal to Wn in order that A is a superset of B. And this is given in the next slide. That is, the degrees of the subset must be less than equal to the degrees of the so-called superset. Let us consider the example. For example, our universal set X consists of again the 5 people Mohan, Sohan, Johan, Abdul, Abraham, and A is defined. Now instead of tall and short, we are defining two general sets in order to generalize the concept of superset of a given set, and the associated degrees are 0.2 with Mohan, 1 for Johan, 0.7 for John, etc., etc. And there are degrees associated with again the same persons in B. Then B is a subset of A, or A is a superset of B, because each of the degree associated with one element in both A and B are such that the degree associated in B is less than equal to the degree associated in A. You can see Mohan's degrees are 0.2 in both. Sohan's degree in B is 0.8, where in A it is 1. Therefore the degree of Sohan is less in B than in A, and rest of the degrees are again either equal or less in B as compared to A, and therefore we can say A is a superset of B. So friends, the basic idea is that in the case of crisp sets, we compare the elements, and if every element of a set B is an element of A, we say B is a subset of A, or A is a superset of B. In the case of fuzzy sets, because every element of the universal set occurs in all the sets, all the fuzzy sets under consideration, we further analyze the degrees, and if the degrees in one of the sets are more than or equal to the corresponding degrees in the other set, then we say the first set is a superset of the later set. I think the idea is very clear. So that is what is meant by this one. Now we will give you another fact about the relation between crisp sets and fuzzy sets. Friends, every crisp set can be thought of as a fuzzy set. However, a fuzzy set may not be considered as crisp set. For example, if we have a crisp set or ordinary set, then for all those elements which are present in the set, in order to make the set as a fuzzy set, or in order to consider the given set as a fuzzy set, we associate degree 1 with all those elements which are present in the crisp set, and we associate degree 0 with the rest of the elements which are not present in the given set. And in this way, a given set may be thought of as a fuzzy set. So, for example, if you have a set X which is universal set having Mohan, Sohan, John, Abdul and Abraham, and if we are having a set of at least graduates, and A is the set which consists of 3 elements, Mohan, Johan, Abdul. These 3 people are at least graduates. They may be master's degree holder, they may be PhD degree holder, etc. But they are at least graduates. Now we want to think of this set A as a fuzzy set. How to think of this as a fuzzy set? What we do? Because Mohan, Sohan, Johan, Abdul are present, we associate degree 1 with them, and the 2 elements which are not present in the set A, namely Sohan and Abraham, we may associate degree 0. And therefore the set A, which is a crisp set, can be thought of as a fuzzy set by associating degree 1 with those which are present and degree 0 with those which are not present. So this is one of the ways of considering a crisp set or a normal set as a fuzzy set. However, a fuzzy set may not be considered or cannot be considered as a crisp set, as can be shown from the next example. Now for this purpose, what we do? We associate degree of educatedness with people having various degrees. For example, degree of education with a person with PhD degree holder may be associated as 1. Degree of education with a master's degree holder may be given as 0.85. Degree of education with a bachelor's degree holder may be given as 0.6. Degree of education with a person having 10+2 level education may be associated as 0.4. Degree of education with a person with 8th standard pass may be associated as 0.1. And degree of education which is associated with a person with less than 8th standard may be 0. Now let us think that C is a set in which Mohan is a master's degree holder, and therefore the number associated with Mohan is 0.85. Sohan is a 10+2, and therefore the degree associated with Sohan is 0.4. Johan is actually a graduate, and therefore the degree associated with Johan is 0.6. Abdul is a PhD degree holder, therefore the degree of educatedness associated with Abdul is 1. And Abraham, who is not even 8th class pass, is associated degree 0. Now this is a fuzzy set. Now can we convert it to a crisp set? No, because the degrees associated are different from zeros and ones, and therefore we cannot consider this set as a crisp set. Friends, we'll think of other concepts corresponding to the fuzzy and crisp set relationship. In context of fuzzy sets, we have a new concept, that of sports set. If we go through our examples, we will find out that a person who is not at all tall is also included in the set of tall persons, of course with degree 0. Now it is very artificial. Artificial in the sense that even if the fact is very well known, please, you need not look at the slide, even if it is known to us that Abdul is, please need not look at the slide. What I was saying is that despite the fact we know Abdul, who is 4 feet something, and any person below 5 feet is not to be considered at all That is, the degree of tallness associated with Abdul was 0. It is artificially, that is, Abdul is artificially made as a tall person, of course with degree 0. What I mean to say through this is that we may drop all those elements from a fuzzy set whose degrees are 0, that is, those elements definitely don't belong to the concept in our mind. So after dropping all those elements whose degrees are 0, we will be getting a new set, rather a new fuzzy set, in which the degrees are non-zero. And this is very natural way of considering a fuzzy set also, that is, those elements which have degree 0 should be dropped out, and whatever is left is called a sport set of fuzzy set. That is, after dropping those elements whose degrees are 0, and out of that we make a set by disassociating the degrees, we get a set which is called sport set. For this purpose, let us look at the slide. Now in the case of exam, C is a set in which degrees associated with Mohan, Sohan, John, Abdul and Abraham are respectively 0.85, 0.4, 0.6, 1 and 0. And as I mentioned just now, if a degree is 0 associated with a particular element, then that is artificially placed in the sense, it doesn't make any sense. So if we drop Abraham from it, and then we collect all the elements without their degrees, we will be getting the set C, Mohan, Sohan, Johan and Abdul. This set C is called the sport set of the given fuzzy set in which all the 5 elements are there. So, to repeat, I say that for a given set, for a given fuzzy set, first of all we drop all those pairs of elements and associated degrees whose degrees are 0. Then we drop the degrees also. In this we will be getting a crisp set, which is called the set of sport for the given fuzzy set. Fuzzy singleton. Sometimes we are interested in sets which have a single element. I clarify through an example. For example, we define the old as the if a person is of age 20 or less, then he has degree 0. And the degree of oldness is 0.2 if the age is between 20 to 25 years, and so on. We go on increasing the degree of oldness with the increase in the age. Now suppose Johan is 23 years old and all others are below 15 years. So you can see that Johan will have degree 0.2 associated with him, but rest of the people will have degree 0 associated with them, because the age is, each of them is of the age less than 15 years, whereas degree associated with everybody vis-a-vis oldness is 0 if the age is less than 20 years. So in this particular case you can see the set, if defined as a fuzzy set, then will be defined something like that: Mohan with associated degree 0, Sohan with associated degree 0, Zohan with associated degree 0.2, Abdul with associated degree 0, Abraham with associated degree 0. But as mentioned earlier also, that when the associated degree 0 is 0, then in that case actually those elements don't have any of the characteristic of the definition under consideration. That is, they are not at all old. We drop them in order to determine the sport set. So if we drop all those elements whose associated degrees are 0, then we are left with Johan 0.2. And if from this fuzzy set we drop the associated degree, we get Johan. So such a set is called fuzzy singleton, in the sense that there is only single element whose degree is non-zero, rest of the elements have their degrees 0. Now friends, so far I have discussed the concept of subset, superset. I have discussed the concept of singleton set in respect of fuzzy sets. But as I mentioned earlier also, that the various operations like intersection, union, complementations are defined and used on crisp sets in order to solve our problems. Now, how to generalize those two fuzzy sets is what we are going to discuss now. Now, the basic idea or the intuition or intuitive idea about how the intersection of two sets should be defined, how the union of two sets should be defined, how the complementation of a particular set should be defined in the case of fuzzy sets should be already clear. But still, we will be always getting our basic ideas from the crisp or the classical sets. So from the classical sets, let us consider what is meant by the union of two sets. In the classical sense, if A and B are two given sets, then what we do? We just combine the elements of the two sets in the form of a set, and if there is any duplication, we drop. That is, A union B is larger, and which contains every element of A and every element of B if the union under consideration of those two sets A and B is there. But there should not be any other extra element. How to carry out this notion of enlargement of the set in the case of fuzzy sets? And as we discussed in the superset, a set may be enlarged by enhancing its degree. So as we know, A union B is the smallest set which contains elements both of A and B. How to generalize it to fuzzy? That is, we take the maximum of the degrees of each element in the union in order to enlarge the given two sets A and B. So what is the possible definition for union of two fuzzy sets? That because all the elements of the universal set occur, only the associated degrees are different. What we do, for each element we take the maximum of the two associated degrees in two sets, and whichever is maximum is the associated degree in the union. That is the basic idea, and now by this time our intuition also should help us that this should be the correct definition. Similarly, in the case of intersection, what is the idea? In the case of crisp sets, that is, it is the set of those elements which are in both A and B. That is, A intersection B becomes a smaller set generally, in which the elements are present only those ones which are in A as well as in B. Now, how to carry out it in the case of fuzzy? In the case of fuzzy, this situation will be achieved if we take the lesser of the two degrees for each element in the two sets. So we create a new set. For two given fuzzy sets A and B, we create a new set C, in which all the elements of the universal set are present. However, the associated degree for each element is the lesser of the two degrees which are there for the element in the two given sets. Similarly, in the case of complementation, as I explained in the case of tall versus short, taller a person, lesser is the degree of the person as a short person. So what we do, we subtract the degree associated with a particular element from 1 in order to get its degree in its complement. So once these ideas are explained, let us have some examples for this purpose. Anyway, we can understand the basic ideas, and in this particular case, let us take the example. Please look at the slide. Let us have two sets C and F. Now we are going to explain these two through these two fuzzy sets C and F. What is their union? What is their intersection? What is the complement of one of these two sets? In the case of C union F, I said because we want a larger set, larger than these two, but smallest among all those sets which are larger than C and F. What we should do? Take one by one each element, compare their degrees in the two, and whichever is maximum we should take as the new degree in the new set. So Mohan, first of all we pick up, in C its degree is 8.85, in F its degree is 0.75, and because 0.85 is more than 0.75, so in the new set, which is going to be called the union of these two sets, we associate 0.85 as the degree of Mohan. Next we come to Sohan. Sohan has degree 0.4 in C and 0.6 in F, and because 0.6 is more than 0.4, therefore the degree in the union which is going to be associated with Sohan is 0.6. Johan has degrees associated with it in the two sets C and F equal to 0.6, and therefore again Johan will have in the union the degree 0.6. Similarly for Abdul, the degree associated with Abdul in C is 1, whereas 0.8 is the degree associated with Abdul in F, and the larger of these two is 1, therefore the degree 1 is associated with Abdul in the union of the two sets. And similarly we can handle the case of Abraham. When we are discussing or when we are considering the complement of intersection of these two sets, then what we should do? We should take the minimum of the two, and just I take one of these, say Abraham we take, Abraham has degree 0 in C and Abraham has 0.3 degree in F, and the minimum of 0 and 3 is 0, therefore the degree to be associated with Abraham in the intersection of the two given sets is 0. Similarly we can determine the degrees of the others which are to be associated with the intersection of the two sets C and F. Friends, next I will discuss what is meant by the complement of C. For this purpose, what we do, in order to, as I explained earlier also, how good as a person is, how good a person is in terms of the reverse property. The reverse property will be good if its degree otherwise is less. If a person is very tall, we say with shortness, he should have very less degree. So in order to get the complement, what we should do, we should subtract its degree from 1. And in the case of C, what will be C complement? The C complement, Mohan already has 0.85 as degree, and therefore its degree in its complement should be 1 minus 0.85, that is 0.15. Please look at the slide. Similarly, because Mohan has degree 0.4, therefore Mohan's degree in complement should be 1 minus 0.4, which is 0.6, and so on and so forth. So friends, we have considered 3 very important operations on fuzzy sets corresponding to the operations on crisp sets. Now next we will consider some of the properties of these operations on fuzzy sets vis-a-vis the properties of these operations on the crisp sets. In the case of crisp sets, we know the union is commutative, the intersection is commutative, and like that. What is the situation in the case of fuzzy sets? Well, it can be verified that in the case of fuzzy sets also, the operation of union, the operation of intersection are commutative. Why? Because while taking the operation of union, what we do? We take for each element the maximum of the associated degrees in two sets A and B. Now the maximum of the associated degrees will be the same whether we consider A as a first set or B as a first set. Because whether A is written first or A is written later on, the associated degrees are same, and the maximum of the associated degrees for each element will remain same whether A is written first or A is written later. But we can give a general argument or a formal argument by which we can show that whether you take A first or B first, the A union will be the same. So A union B is equal to B union A. Similarly, you can show that A intersection B is equal to B intersection A, because ultimately what we are doing. Similarly, associativity, that is A union B, if you take first and then take the union with C, or vice versa. Similarly, distributive laws. Each of these laws hold valid even for fuzzy sets, which otherwise hold for crisp sets also. De Morgan's laws. You know what are De Morgan's law, that the complement of union is equal to intersection of their complements and vice versa. But it can be also again verified that De Morgan's laws are also valid for fuzzy sets. Involution. We know A complement is A, and this is also true because while taking the complement, what we are doing? We are subtracting the associated degree from 1. But if we subtract a degree associated from 1 and again we subtract the new degree from 1, we will be getting the original degree. Therefore, from this also it can be concluded that A complement must be equal to A. It is called the involution property. Idempotence. You know that if the union of a particular set is taken with itself, then it comes out the itself also. It is true in the case of crisp set, it is also true in the case of fuzzy sets also. And identity also, you know. Friends, in the case of fuzzy sets, what is meant by an empty set? Though the idea must be intuitively clear, but we have not explained it in this lecture formally or explicitly. What do we mean by an empty set? In the crisp set sense. In the conventional or crisp set sense, a set is empty if it does not have any element. But in the case of fuzzy theory or fuzzy sets, every element of the universal set must be present in every fuzzy set. Only it should have associated degree. And if every element in a particular fuzzy set has associated degree 0, what does that mean? That means every element in that fuzzy set does not have the property that the degree of having that particular property is 0. That is, none of the element has any part of the property. So, in the fuzzy sets, a set is said to be empty if the degree associated with each element is 0. And now, using this concept of empty set, we can very easily prove what is written on the next slide. Please look at the slide. We can very easily show that the union of an empty set with any set must be that any set, because while taking the union we are taking the maximum of the degrees in A and degree in empty set, but the degree in empty is 0, so the maximum of these two degrees will be the degree in A, and hence A union empty set must be A. Similarly, you can show A intersection empty is equal to empty, because while taking intersection of two fuzzy sets, we take the minimum of the degrees for each element associated in the two sets, and because any degree in A and degree in phi is 0, therefore and all the degrees are non-negative, therefore the degree 0 will be the minimum of the degrees of a particular element in A and empty, and hence it can be very easily shown A intersection empty set is A. Similarly, A union is equal to U, universal, where U denotes the universal set and something like that. Formally, the definition is given of the universal set. Universal fuzzy set is a set in which the associated degree with every element is 1, and a set is fuzzy set is said to be empty if the associated degree with each element is 0. Friends, there are some operations which are not there in the case of crisp sets, but they are unique to only fuzzy sets. So now we will consider some of the operations which are not talked about in the case of crisp sets. However, these operations are discussed only for fuzzy sets. Let us have a look at the next slide in order to know some of these operations. Concentration. Concentration is actually something like very tall. Whenever you are discussing tall, and then you need to discuss very tall persons also, naturally the very concentrates the property of tallness. But this means that the degree should become less. Because if a person is having degree of tallness as 0.5, degree of very tallness will become something less. So in order to capture such notions of very tall, very sweet, very beautiful, etc., what we do? We will be reducing the degree. And we will be reducing the degree in a systematic way. And one of the systematic way of reducing the degree is because every number is between 0 and 1. We just square those. We know the square of a number between 0 and 1 is less than that number itself. So this is one of the way, that is concentration is nothing else but accentuating the degree of the property under consideration. If tall is being discussed, then very tall becomes under consideration, and it is captured through concentration. So please look at the slide. The slide says that concentration of a particular property A is obtained by associating the square of the degree in A with the element in the new set which is to be called con A. For example, if A is the degree of A is the set of tall persons, and associated degrees with Mohan, Sohan, John, Abdul, Ibrahim are 0.5, 0.9, 0.7, 0 and 0.2. What will be concentration A? Concentration A will be denoting the set of all very tall persons. And in that case, what we do, we take the squares of the associated degree. That is, Mohan is associated 0.5 square, which is 0.25. With Sohan, in the very tall person's set, the degree will become 0.9 square. Similarly with Johan, earlier the degree was 0.7, which was associated in A. Now the degree associated with con A will become 0.49, and so on and so forth. So this concentration operation is about increasing the intensity of the property under consideration. Very tall, very small, very hot, very cold, etc. Instead of talking hot, small, tall, etc. The opposite of this is called dilation. That is, in some of the cases, when you are already considering very tall persons, from the very tall persons we like to discuss the tall persons. So what we will be doing, we should increase the associated degrees, and one of the ways of increasing the degrees when the numbers are between 0 and 1 is to take the square root. And actually dilation doesn't require much explanation, because it is just the opposite of concentration. So friends, you can see that dilation in the case of given set will become just by taking the square roots. The square root of 0.5 is something, 0.7 something, etc. So this gives us the dilation. So concentration and dilation are the two operations which are considered for only the fuzzy sets. Friends, there are a number of other issues and applications also in this in respect of fuzzy sets, which we will be discussing in some of our later lectures. In the meantime, we may have a look at some of the references which are useful for us, and for that purpose, please look at the slide. Some of the references are given. For example, chapter 5 of the Fundamentals of New Artificial Intelligence Beyond Traditional Paradigms by Toshinori Munakata. It is really very good book, published by Springer in 1998. Then another very good book is a first course in fuzzy logic by Huang T. Nguyen, etc. CRC Press. It also gives a number of applications also. So friends, with this we end our today's lecture on. We will be continuing our discussion of fuzzy in some later lectures. Thank you.